Welcome, students. This tutorial will lead us through more practice and hopefully give us some clarity with particulate diagrams regarding solutions, and then when those solutions are mixed, creating a precipitate. So, digging in. Comparing these. So these are to represent to us snapshots of inside maybe a test tube or a beaker. And we know all potassium compounds are soluble. So this must be in aqueous solution. So we know that our water molecules would have their ears or the positive side near the anion, and then the chin side, the negative portion of the molecule toward the cations. But just for clarity, we have removed the water molecules. If we examine, we know that for every one formula unit of potassium bromide, we get one potassium ion for every one bromide ion. And if we check, the 1-to-1 ratio is respected. Here, we know all sodium compounds are soluble. And when this dissociates, we get 2 sodium cations for every 1 carbonate anion. So 2 sodiums, 1 carbonate, 2 sodiums, 1 carbonate. So I'm just using these to illustrate that a solution needs to, 1, respect the ion ratios within the formula, but also total positive should equal total negative. And so you're diagramming a neutral solution. Here, this is just illustrating 1 formula unit dissociated. We have 2 aluminum plus 3s for every 3 sulfates. All right. Now, moving from here, you are going to be given a scenario and then asked to draw. So if you would like to pause before I do my explanation and you try to come up with the answer, I would encourage that. So first, imagine that we are given this particulate diagram, and we are actually told that this is representing a 3-molar potassium bromide solution. We know it's completely soluble and dissociated. We have 1 cation for every 1 anion because of the 1-to-1 ratio. But if I take a look and just count up the cations and the anions, that is something that I would suggest to be an option. Is sometimes if we can count the number of cations and anions, then if we're asked to do anything else, it just kind of leads us in the correct direction. So if we come up with numbers. All right. So I have 1, 2, 3, 4, 5, 6 potassium ions. So we should have 6 bromide. 2, 4, 6. So 6 cations and 6 anions are representing a 3-molar. So if I am asked to draw a 1-molar silver nitrate, how nice, that +1 and -1. So if 6 cation plus 1s show 3 molar, I need 1/3 of this. So I would show 2 silver ions and 2 nitrate ions. So whatever ratio is shown here to represent 3 molar, I need 1/3 of the same ion ratio here to show 1 molar. So we would draw them as homogeneous as we can, making sure that we are identifying these as ions. And then 2 nitrates. All right, so we've accomplished that. However, what if they are not 1-to-1 ion ratios or the same ion ratio? So, oopsie daisy, I have the same. Sorry about that. All right, so what if we have 3 molar and 1 molar? So again, 1/3 of the concentration. However, it's not the same ion ratio. We are starting with 6 potassium ions and 6 bromides. All right. So we have 2 sodium 1 plus or plus 1 for every 1 carbonate. Okay. I think it is easier to compare, for initial thinking's sake, these same charged ions. All right. So to represent 3 molar, I have 6 potassiums. Well, for every 1 of these, I get 2 sodium ions. Let me think. So this is actually a total of positive 2, is it not? As well as this is a negative 2. All right. Well, to represent 3 molar, it's a total of positive 6. And then balancing a negative 6 with plus 1 and minus 1. So I need to represent a third. And so a third of positive 6 and negative 6 would be 2, right? So 2 of my sodiums deliver the positive 2, and 1 of the carbonates deliver the minus 2. Let me go ahead and draw that and then just double check my thinking. All right. Because this formula has 2 sodium ions for 1 carbonate, I could look at it as these 2 are delivering a positive 2, and this one a negative 2. 6 plus 1s are being shown to equal or to represent 3 molar. So a third of the charge that I need, a third of the charge would be a positive 2. Well, 2 sodiums deliver that and 1 carbonate delivers that. So I could look at the total charge ratio. The total charge is representing that. The total charge that is representing that. Okay, let's take a look at this. Okay, 2 molar sodium carbonate. And I have 2 sodium ions for every 1 carbonate. Okay, in this drawing, I have 2, 4, 6, 8 sodium ions. And then I should have 2, 4. All right. So a total positive 8. Oh, what am I saying? I'm so sorry. Yeah, it is a total of positive 8. And then 4 would give a negative 8. I'm sorry. So if we're looking at, our charges. So positive 8 and a negative 8 are representing 2 molar. So half of that, I would need a positive 4 and a negative 4. So because for every 1 KBr, there's 1 potassium ion, 1 bromide, then to deliver the positive 4, I will have 4 potassium ions and 4 bromides. Okay, can we go the opposite direction just to double check ourselves? So 1 molar, if we're representing that, oh, I don't want to have those touching because that implies bonded, right? So 2, 4, and 2, 4. So if I am doubling the concentration, I need a total doubling of charge. And so how many ions per the formula will deliver the positive 8 and the negative 8? Well, I will need, let's see, a total, of 8 sodium ions, right? Each gives plus 1. And I will need 4 carbonates. And that's what we have. Okie dokie. So what we also could be confronted with is representing a reaction. And we're just going to look at precipitation reactions. So completely soluble sodium, and you're being told this is soluble, and we are creating that precipitate, and then these will be liberated ions. We're not given any concentrations, so we would just look at, okay, so this solution is providing 2 aluminum ions and 3 sulfate. Well, I know those aluminum ions are going to, as long as there's enough carbonate, are going to precipitate with that. For every 2 aluminum plus 3s, I'm going to react 3 carbonates. And it's insoluble. They will attract each other, and I want to show them touching. And we're just going to do the best job that we can. I wouldn't put cation next to cation, or, you know, we're going to do the best we can without really showing geometry here. So for every aluminum, 2 of them, I have 3 carbonates. So maybe I'll put a carbonate there. And then another 2 aluminums. And again, I want to show them as touching. And a carbonate. And a carbonate. We just want to be as clear as we can. All right. Oh, sugar. Oh, yeah, we're good. No. Oh, my goodness. I went to town. I made too much product. Holy smokes. 2 of these react with 3 of these to make 1 formula unit. All right. So there. Not 4 aluminums. All right. So carbonate, carbonate. I will put it here. Carbonate. But we want to definitely show touching. And I would draw it toward the bottom, because we've seen time and again, when we create an insoluble solid, often gravity pulls it as they collect into larger and larger pieces. So what's going on with the remaining? They're spectators. So these 6 sodiums, they do not react. They will remain liberated in solution. One, two, three, four, five, 6. And then my 3 sulfates. And that, oh, I drew these too big, huh? So that will, draw that smaller. All right, there we go. And we get the ratio correct. 2, 4, 6, and then this is -4 and -6. So these have collected and bonded. These are separate ions that are just spectators in this case. All right. Well, what about this scenario? Same reaction. Oh, but I can directly see I'm starting with more ions here. So I have 1, 2, 3, 4 total aluminum plus 3s. Well, let's see, I have, only 3 carbonates. Remember, every 1 or 2 aluminum plus 3s will bond with 3 carbonates. So the sodium carbonate, or the carbonate, is the limiting reactant. I'm only going to create the same number, 1 formula unit. I run out of carbonate after the first one is formed. And they're aluminum plus 3, and then maybe another carbonate there. Okay, and everything else will then be in excess. So I have, let's see, 2 remaining aluminums. Okay. Only 2 of them reacted, so I have 2 remaining. And then we have 1, 2, 3, 4, 5, 6 sulfates. Just for sake of time, I'm going to really draw these quickly. I'm sure you can draw them much more neatly. So another sulfate, 4, 5, and then 6. And then all of our sodiums, 2, 4, 6. It's a little easier to draw. 2, 4, 3, or 1, 2, 3, 4, 5, and then 6. And let's check to make sure that we're completely balanced charge-wise. So these are bonded, not touching, and I have 2, 4, 6, plus another 6. So a total, a positive 12. So I should have 2, 4, 6, 8, 10, 12. Excellent. All right. Now, the other scenario is, what if we have to work backwards? What if we are shown, oh, I made 2 of these. Well, net ionically, we must be reacting lead plus 2 with 2 chlorides. And the lead ion must have been originally dissociated from nitrate, and the chloride was delivered with potassium. So, doesn't matter what you put where, this would have begun as a solution of KCl, and this would have begun as a solution of PbNO3 2. All right. Well, how did I get these 2? Well, I must have 2 maybe of these formula units. Let me see. So these 2 lead ions would have come from this. Well, 2 lead ions, I would have 4 nitrates. 1, 2, 3, 4. There we go. So originally 2 lead plus 2s, and then 4 nitrates. All right. So now I have 1, 2, 3, 4. Oh, I see a 5th chloride. So let me see. Do I have 5 potassium ions? 1, 2, 3, 4, 5. Ah, so the lead was a limiting reactant. So I have 1 excess chloride. So, but the other 4 react with the lead plus 2. And then 5 potassium ions. I would do a double checking to make sure that all of these are neutral. Your total positive equals your total negative. If you want to double check to make sure that you get this from these combinations. Hopefully, this gives us some good practice and shows us all the scenarios of particulate diagrams with solutions and precipitation reactions.